So in this lesson, we're going to move away from row operations a bit. We'll come back to it, have no fear. But we're going to talk now about some matrix operations and also some things that can be done with them. And don't worry, before we're done today, we will still be doing echelon form and all that stuff. It's not going to go away. But first, let's just talk about some operations. So this is a matrix. We've seen matrices. It's not a big shock. I just want to make sure we're kind of using the same terminology here. So first off, the 5, circle it right there. That 5, I'm going to call that entry 1, 2. Now, don't say entry A sub 12, okay, because it's not 12, it's a 1 and a 2. And it's 1, 2 because that 5 is in the first row and the second column. So it's in row 1, column 2. So we'll call that A1, 2. The entries A11, A22, etc. are called the main diagonal. So the entries where the row number and the column number are the same. I'm referring to that as the main diagonal. Honestly, I don't even remember if that's normal for other people or if I just kind of made that up. But when I personally refer to the main diagonal, that's what I'm talking about. A diagonal matrix. Okay. So a diagonal matrix is a square matrix. Remember, square means the number of rows is the same as the number of columns. But it's specifically one where the main diagonal, it can be whatever, it doesn't really matter. But the point is all the other numbers are zeros. So this idea of a diagonal matrix. Now, we're really not going to spend much time. I don't even know if we're going to spend any time on that with that today. But it's worth defining that now because certainly in later chapters we'll come back and talk about diagonal matrices. So I want to make sure we know what we're talking about. So diagonal matrix right there. Okay, two matrices are equal if they have the same order and if the corresponding entries are equal to each other. By the way, the next several slides here are going to be very much, they're going to feel familiar because when we first talked about vectors, we talked about a lot of the same things we're about to say for matrices. Of course, a vector is just a matrix with only one column, but we said two vectors are equal if they're the same size and if they have the same number, the entries are all the same as each other. I'm saying the same thing about matrices. Adding and subtracting matrices means that performing the operations on corresponding entries. Again, that sounds familiar because we said the same thing with vectors. So if we add two matrices together, just add the corresponding pieces. The only way that works is if they're the same size. So you can only add two matrices or subtract if they have the same number of rows and the same number of columns. And then when you finish with that addition or subtraction, the result will be the same size. So for example, we have a 2 by 2 matrix and a 2 by 2 matrix. And so when I add those together, I'm going to get a 2 by 2 matrix, right? The size of the two matrices being added have to be the same, and the result will be the same size. So I'll take the upper left entry plus the upper left entry. So the upper left entry for this matrix plus the upper left entry for this matrix. -1 plus 1 is 0. 2 plus 3 gives me a 5. 0 plus -1, and 1 plus 2. Okay, so again, adding two matrices, it's just like adding vectors. It's exactly what we would like to happen. Subtracting, same deal. Mostly just have to be careful to subtract each of them. So we'll do 0 minus -3, 1 minus 1, -2 minus 4, 1 minus 0, 2 minus 2, and 3 minus -5. So again, you just, for subtraction, just don't forget, even if it's negative, make sure you subtract the negative number. We also want to talk about scalar multiplication, right? Scale multiplication means multiplying a matrix by a constant. Again, we've had this conversation when it comes to vectors, and just like with vectors, multiplying by a scalar just means every entry inside gets multiplied by that scalar, whatever that happens to be. A few properties of matrices. You don't need to memorize these, but basically this says that the commutative property applies. You can switch the order and still get the same result. The associative property, you can add them. If you're adding three things, it doesn't matter what order they're added together, you'll get the same result. Here, this 0 would refer to the 0 matrix. So taking a matrix plus the 0 matrix results in the original matrix again. A couple of distributive properties, and I guess this would be the associative property for scalar multiplication. Anyway, I don't expect you to have any of these memorized. Just understand that a lot of the same things that we've seen in with just plain old adding numbers still applies to adding and subtracting and scalar multiplication for matrices. So a real quick example here. Let A be this matrix and B is this matrix. So again, 3A just means multiply every single entry by a 3. That's it. Just multiply every entry by a 3, no biggie. And then if I would do 3A minus B, I don't even know if I want to bother doing this, but 3A we've already found. And then we're going to subtract from that B. And so if I do the subtraction, 6 minus 6, 6 minus 0, 12 minus 0, negative 9 minus 1, 0 minus negative 4, negative 3 minus 3, 6 minus negative 1, 3 minus 3, and 6 minus 2. So I zip right through that because, I mean, it doesn't really, this is exactly like matrix when we were working with vectors. Okay, now we need to talk about matrix multiplication because this now is where things are going to change. Um, First of all, I want to point out we did not talk about multiplying a vector times another vector because actually there are different ways to do that. We'll touch upon that a little bit later on in the course. And if you're taking physics, you'll get into that. When you take vector calculus, usually part of a Calc 3 class, you'll get into those also. But so I'm not concerned with multiplying two vectors at this point. But when we multiply two matrices, it is not as straightforward as we would like it to be. When multiplying two matrices, we are going to take a row from the first column and multiply it by a column. I'm sorry, take a row from the first matrix and multiply it by a column from the second matrix. Now, the word multiply there is, I'm using that kind of loosely, but I'll show you what I mean by that. In order for this to make sense, in order to actually multiply two matrices, the sizes have to match up. Now, that doesn't mean they're the same size. Here's an example where multiplication would work out. If A is a 4 by 3 matrix and B is a 3 by 7 matrix, in order for this product to even be possible, these two numbers have to be the same number. So those are both 3's. So if those two numbers are not the same number, it is not possible to multiply the two matrices. Of course, I'm not going to ask you, hey, do a multiplication, but just kidding, it's not possible. I wouldn't do that. But just understand that in order for the multiplication to make sense, those middle numbers have to agree. And whatever those outside numbers are, that's going to dictate the size of the result, the size of the product. So this is what we mean. This is what I mean by the orders have to match up. They don't have to be the same order. There are some cases where they can be, but that's certainly not necessary. But the middle numbers there have to agree. Okay, let's talk about how to actually do the product. So let's consider this product of two matrices. First of all, please note that this is a 2 by 3 matrix, and this is a 3 by 2 matrix. The inside numbers are both 3, so that's great. And the outer numbers are 2 and 2. So when I do the product, it's going to be a 2 by 2 matrix. So that's the first thing, is just identifying how big our answer is going to be, how big a matrix we're going to end up getting. So here's the plan. I'm going to take the first row of the left matrix and multiply it by the first column of the right matrix. Now, when I say multiply, again, I'm using that word loosely. If any of you have learned the idea of a dot product, we're going to use the dot product. Now, if you haven't heard of dot product, don't sweat it. We're going to get to that later in this course. We will definitely talk about it. But just understand that that's what I mean here when I say multiply. But if you haven't seen dot product, don't sweat it. Here's how we're going to do it. So I'm going to take my two rows. Now, it might be a little bit hard to see, but I've got some colors going on. So the top row, so in the first matrix, the top row is red, the bottom row is blue. In the second matrix, the first column is green, and the second column is maybe brown, maybe maroon. I don't know. I think it's brown. Anyway, so as I said, I'm going to take the top row and multiply it by the first column. So I'll do red times green. And so when I do that, because those numbers agreed, that means that there's the number of entries in this row is the same as the number of columns in this number of entries in this column. And so I'm going to pair them up. So the 1 pairs up with the -2, and I just multiply those two numbers. The 0 pairs up with the 1, so I multiply those numbers. The 3 pairs up with the -1, and I multiply multiply those two numbers. I take all those products and I add them together, and I get a -5. Now notice that that was row 1 multiplying column 1, and so the result goes in row 1, column 1 of my final result. Let me erase my circling here. That was row 1 times column 1. Now let's do, now let's do row 1 times column 2. So now I've got the red row times the brown column. Again, matching up, basically taking the 3 entries of the red row, matching them up with the 3 entries of the brown column, and multiplying each of those pairs and adding the results. And because that was row 1 times column 2, the result goes in row 1, column 2 of my answer. And I just keep doing this. Next up, I've got the blue row times the green column. So row 2 times column 1. When I get that result, it goes in row 1, column 2. I said it wrong. I'm sorry. That was row 2 times column 1. So the result goes in row 2, column 1 of my answer. And then finally, we have the blue times the brown. So row 2 times column 2. The result goes in row 2, column 2 of my answer. We'll do a few examples of this, but this is what I mean by matrix multiplication. All right, let's look at another example. And this one I don't have all spelled out. We'll talk through this one. This is a 2 by 2 matrix, and this is a 2 by 3 matrix. Once again, those middle numbers have to be the same, and they are. And so when I do the product, the result is going to come from those outside numbers, the 2 and the 3. And so my answer is going to be a 2 by 3 matrix. So I expect there to be 2 rows. I expect there to be 3 columns. So let's start with row 1 times column 1. So match them up. 1 times -3, 2 times 4. So multiply the things I drew arrows to. So -3 plus 8 gives me a 5. And that was row 1 times column 1. So my answer goes in row 1, column 1 of my answer. Okay, next up, let's do row 1 times column 2. But you know what, let me erase that too. Okay, so now I'm doing row 1 times column 2. So now I get 1 times 1 and 2 times 8. Add those together, so we get 1 plus 16 gives me 17. And again, that was row 1 times column 2. So that answer goes into row 1, column 2 of the answer. Row 1 times column 3. So I got the 1 times 6 and the 2 times 3. So we get 6 plus 6 is 12. Now I'm ready to move on to the second row times the first column. So row 2 times column 1. Pair them up, so 3 times -3 and 4 times 4. So -9 plus 16 is 7. Row 2 times column 2. So 3 times 1, 4 times 8 gives me 35. And the last one here, row 2 times column 3. 3 times 6 and 4 times 3. So 18 plus 12 is 30. So this is the result of this product. And as I said, we'll do some more of these, but really more than anything else, this takes practice. It definitely takes just doing a bunch of these problems. You might even want to look online and find some more matrix multiplication examples just so you can get some practice, because it's definitely worth it, but it takes practice. Okay, here's some properties of matrix multiplication. The associative law. So again, the associative law says the order doesn't matter as long as the order doesn't matter that you do the product. Of course, this only makes sense if notice that the statement at the top says A is an m by n matrix. I don't really know why they even. Oh, I guess the last property required that doesn't matter. And then B and C just have sizes for which the indicated sums and products are defined, right? Because the size of A and B and C dictate whether an answer is even possible for some of these properties. These are both a distributed property. We're going to explain in a minute why there are two of them. Here we have the scalar product. Basically, it doesn't matter whether R is multiplying A times B, or R is multiplying A, or R is multiplying B. They're all the same. And this is the identity matrix, basically saying if you multiply the identity times any matrix, you get back the original matrix A again. The only reason that, again, they're different statements is because A is an m by n matrix. This I is m by m. Remember, I is always a square matrix, and A is m by n. This has to be an m by m identity because those have to agree. And for the same reason, this one has to be an n by n identity for this to work. Anyway, there is one property that is not on this list. And I want to show you what it is by considering an example. Let's do this product. So first of all, it's 2 by 2 times a 2 by 2, which results in a 2 by 2. Fine. So I'm going to do the first row times the first column. 1 times -3 and 2 times 4 gives me 5. I'm realizing now this is the same two matrices as the last example, just with the last column missing. So I'll just run through this real quick. We got 17, 7, and 35. These are the same work, just missing some of the numbers. Now, the next thing I'd like to do is try the same product, but switch the order. It's the same problem, but I'm switching the order that we're multiplying. In this case, we can do that, right? Because it was a 2 by 2. Switch them, it's still a 2 by 2. That's perfectly acceptable. So if I do this product, again, first row times the first column, it'll be -3 times 1 and 1 times 3. -3 plus 3 is 0. Well, already I'm noticing a difference, right? I'm not getting the same answer as the last one. And in fact, we're going to find that none of these are the same. Let's see, this is -2, -6 plus 4. The next one will be 4 plus 24 is 28. And the last one, 4 times 2 and 8 times 4. So 8 plus 32 is 40. So what we found in these two examples is if you switch the order, you might not get the same answer. Okay, and that's actually why there are two different distributive properties here. One distributive property is where the thing being distributed is on the left, and the other is where we're distributing on the right. But notice when I do this product, it's A times B. Well, it has to be written as A times B. Here, when I distribute from the right side, now B is multiplied by A, so we write B times A. To summarize here, in general, A times B is not the same as B times A. In other words, there is no commutative property for matrix multiplication. And not only do we not get the same answer, sometimes if you switch the order, you may not even be able to do the problem. For example, let's say that you're doing A times B, and it's we had the example earlier, 4 by 3 and a 3 by 7. No problem. Okay, they agree, we get an answer. What if I tried to switch the order that I multiplied them? Well, B is still a 3 by 7 matrix. A is a 4 by 3 matrix, right? I'm just changing the order that I write them. When I switch the order of multiplication, not only do I get a different answer, I get a problem that I can't even do. It's not even possible to be done because this time the inside numbers don't agree. So keep in mind the order that you're multiplying matters, and sometimes switching the order usually it gives a different answer, but sometimes it gives you a problem that's just impossible. So interesting to observe. Cancellation laws don't hold. Cancellation law would say, oh, if you have 5x equals 35, you can just cancel the 5 on both sides and you're left with x equals 7. Well, cancellation doesn't work here. If you have A times B equals A times C, you can't just say, oh, let me just cross off the A's and now B is equal to C. That's not actually true. Um, it is sometimes true, but it's not always true. It actually depends on A, but we'll get into that. But the point is, you can't just cancel the matrix on both sides and expect that B is the same as C. It just doesn't work. And then if A times B is equal to 0, and by the way, A times B is a matrix, so this would be the 0 matrix. It may not be true. Think about, it may not be true that A is 0 or B is 0. Here's what I mean by that. If I told you that X times Y is equal to 0, okay, X and Y are just numbers. If I told you that X times Y is equal to 0, you're allowed to conclude that either X is 0 or Y is 0. Right? Because that's a property of 0. If you multiply two numbers and you get a result of 0, one of them has to be a 0. Well, this third caution here basically says if you multiply two matrices and you get a result of 0, it's possible that both of them are non-zero matrices. And so I guess my point is simply when you're multiplying matrices, don't always take for granted things that are true when we multiply numbers, because sometimes that won't be the case. Okay, one other thing we can do with matrices here is find what's called the transpose. Now, I'm going to tell you right now, the transpose is a little bit silly. And we're going to, as we go through this course, we will see some cases where transpose is kind of sort of useful, but mostly transpose is really silly. It changes a matrix so that the entry in the ith row and jth column gets moved to the jth row and ith column. Yes, I said jth and ith. That's how math teachers talk, I guess. But it's just easier if I show you an example. Find the transpose of each matrix. So we have this matrix. Okay, here's matrix A, and we're going to find A transpose. So let's look at some entries here. Now, let's start with this -1. Notice that the -1 is in row 1, column 2. Well, I'm going to move it to be in row 2, column 1. The 3 is in row 1, column 3. And so I'm going to move it to be in row 3, column 1. So there's my 3. And by the way, an interesting observation, this is in row 1, column 1. Switch those two numbers and you're still going to be in row 1, column 1. So actually this main diagonal, those numbers are not going to move when we find the transpose. Now, you don't need to do this process for every single thing, because an interesting observation here is, notice that the first row of A became the first column of A transpose. Well, that wasn't a coincidence. The second row of A will become the second column of A transpose, and the third row becomes the third column. So finding the transpose is real quick. It's also a little bit silly. We're just kind of rearranging stuff. I don't have a great reason for that. It's just kind of something we do. Let's consider this example, B. Please notice, you know what, let's just do the same thing here. Okay, oh, sorry, that should be B. Let's just do the same thing. Finding the transpose. So the first row becomes the first column. Notice that because the first row had 2 entries, the first column will also only have 2 entries. The second row becomes the second column, and the third row becomes the third column. Notice that when B was a 3 by 2 matrix, B transpose is a 2 by 3 matrix. So that's interesting. And then, you know what, I'm not even going to bother doing this one. It's the same idea. This is a 2 by 3 matrix. So when I find C transpose, I expect it to be a 3 by 2. I'm not even going to bother doing it. It's the same thing, same idea. Some properties of transpose. So first of all, A transpose is just A. In other words, if you were to take the first row and change it to the second column, or sorry, no, that doesn't make sense at all. If you were to take the first row and change it to the first column, that's A transpose. Well, now if you do it again and now take the new first row and make it another first column, meaning take the transpose again, you're basically putting everything back where they started. So doing the transpose twice is basically results in the original matrix. Fine. This says that you can kind of distribute the transpose over addition of matrices, although I don't know if I want to use the word distribute. Basically, it says that if you have the sum of and then you take the transpose, that is the same as first doing the transpose and then adding the results. If you've got a scalar multiple, you can bring it out. That makes sense, right? Because when we multiplied by a scalar, we just multiplied every entry by that scalar. Well, if you rearrange stuff, every entry is still multiplied by that same scalar. So that's fine. This one I think is the most surprising one. If you do a product and then find its transpose, that's the same as first transposing the two matrices and then multiply them, but do it in the reverse order. Now, just purely out of curiosity, I want to see how that works. Let's say that A is a 4 by 3 matrix and B is a 3 by 4 matrix. And so this tells me that AB is going to be, I'm sorry, I want to stick with what I did before. Hold on a second. Okay, so B is a 3 by 7 matrix. Okay, so when I do the product, I get 4 by 7. AB is just a matrix. So when I find the transpose of that matrix, the result is going to be 7 by 4. We saw that earlier, right? The number of rows and the number of columns switches when you take the transpose. Well, let's consider instead, let me see here. When I do B transpose and A transpose, all right, let's think about it for a second. B transpose would be a 7 by 3 matrix, right? Because again, B, the rows and column switches. A transpose would be a 3 by 4 matrix. So notice that in order for this product to work, we had to switch the B's and the A's because again, we still need those inside numbers to meet. And notice that now if I do B transpose times A transpose, my result is going to be a 7 by 4 matrix. And that property D there says these are equal to each other. Well, I haven't really proven they're equal, but at least I've proven that they would be the same size. So just kind of an interesting property of transpose. Honestly, one of the few things that is interesting about transpose, but I guess I'm just being biased. I don't know. Okay, let's get to our second, or to our other topic for today, which is inverse matrices. Okay, so inverse matrices. Let's talk about just what do I mean by inverse before we get into inverse matrices. So think about multiplication, okay? An inverse is the opposite, okay? The opposite of a number. Okay, let's just talk about multiplying numbers, real number multiplication. An inverse is something that would cancel out with another number when we multiply them. So in this example, 2 and 1/2 are what we call multiplicative inverses. And the reason is if we multiply them, they basically cancel each other out. And we're left with 1, which, by the way, we had a name for that. That was called the identity. So 1 is the multiplicative identity when it comes to numbers. So inverses are two numbers that when you multiply them, you get 1 or you get the identity. Well, the same is true for inverses of matrices. The inverse of a matrix A, we're going to write that as, now it looks like A to the negative 1 power. It's just A inverse. In fact, you might remember from, I don't know, pre-calculus maybe, when you saw this notation, we call that F inverse. Same idea. It wasn't a superscript, or it is a superscript. It wasn't an exponent. It was just a notation for inverse. In fact, we did the same thing for sine, right? Sine inverse of x, same idea, that negative 1. So A inverse, and it has the property that when you take A and multiply by its inverse, you get the identity matrix. And by the way, we should write it both ways because as we saw earlier, switching the order of multiplication doesn't necessarily result in the same answer. So the thing about inverses is when you multiply them, you do get the same answer. The result is I. I should mention, and I don't think I have it written here anywhere, but we will only talk about the inverse of a square matrix. I would never talk about a matrix that is not square and say, find the inverse. No, it doesn't work that way. We only talk about inverses of square matrices. So if, oops, there we go. Yeah, if a matrix has an inverse, we say it is invertible, right? That's a real deep definition, I know. If it is not invertible, we call it singular. And oh, I have it right there. Only square matrices are invertible. So we wouldn't talk about it otherwise. Okay, let's start with this. Let's show that these two matrices are inverses of each other. Now, obviously, this is not a big part of this lesson, right? That we're more interested in how do we find the inverse. But let's just start by showing that these are inverses. And again, to show that, we're going to find the product. We're going to find A times B. So -1, 2, -1, 1 times 1, -2, 1, -1. Okay. I'm going to do the product. So we have the top row times the first column. So it'll be -1 times 1, and 2 times 1 is 1. Add them together. The first row times the second column will be 2 plus -2, which is 0. The second row times the first column will be -1 plus 1, which is 0. And the second row times the second column will be 2 plus -1 is 1. We got an answer that was the identity matrix. Great. Similarly, we should also show that B times A, right? Switch them and still show that we get the identity matrix. I'm going to skip that, but you should. When you show that these are matrices, you should check both orders, both orders for doing this product. Okay, now, as I said, our interest is not show that they're inverses. I mean, that's great. We can do that. But our interest is more, here's a matrix, find its inverse, okay? Or here's a matrix, determine if it is invertible, right? That's basically the rest of this lesson is how do we find an inverse? And then after that, how do we determine if a matrix actually has an inverse, if it is invertible or if it is singular? Let's start with 2 by 2 matrices. So to decide if to find the inverse of a 2 by 2 matrix, there's actually a quick way to do it. It requires a little bit of rearranging, but it's basically more of a process than actual computations. If A is this matrix, so it's got 4 entries A, B, C, D, A inverse is going to be this fraction, so 1 over A times D minus B times C. So 1 over this quantity. And then we're going to rearrange the entries of A to create a new matrix. Okay, so we have to multiply by a fraction and we have to rearrange stuff. Notice what's changing. The entries in the main diagonal just sort of switch places. So notice that the D and the A are in different places. The B and the C don't move. They just both change signs. They both become opposites. Okay, and that's the idea, right? This, again, not really any work to do, but this is the process for finding the inverse of a 2 by 2 matrix. Real quick, I want to just observe that quantity of AD minus BC is called the determinant, and we actually are going to look at that during the next lesson. But that AD minus BC is called the determinant. So, and that'll come back again. But please notice it is 1 over that thing that I'm calling the determinant. All right, so let's play around with this. Yeah, we'll come back to that later. Let's play around with this. Let's find the inverse. So once again, to find the inverse of a 2 by 2 matrix, there are 2 things we have to do. First of all, it's going to be 1 over, so it was A times D, so multiply the main diagonal, so 3 times 2 is 6, minus multiply the other diagonal. -2 times -1 is 2. So it's 1 over, multiply the main diagonal minus multiply the other diagonal. And then that's going to multiply by a new matrix that comes from rearranging the old one. The main diagonal, those 2 numbers just switch places. And the other 2 entries stay put, but they change sign. So +1 and +2. And let me clean this up just a little bit. So we get 1/4 times 2, 1, 2, 3. I'm happy with that answer, but if you want to be a little more fancy, you can bring that 1/4 inside. So we get 1/2, 1/4, 1/2, and 3/4. Again, I don't care if you do that. It doesn't matter. Okay. Cool. Let's look at this example. Not quite the same example, very similar, but small changes here. So B inverse is going to be 1 over, so again, multiply the main diagonal, 3 times 2 is 6, minus multiply the other diagonal, -6 times -1 is 6. And I could find the new matrix, but what I want to notice is we're dividing by 0. Well, that's not good. Clearly, we're not allowed to divide by 0, so what this tells me is that B is singular. Or you could say a B inverse does not exist. By the way, if that was a possibility, the directions would say find the inverse if possible. I might add to that, if not, explain why it is not possible. But yeah, just be aware that it's possible. If you divide by the 0, you know that there is no inverse, that matrix is singular. Okay, this is a neat little trick for 2x2 matrices. Now, before we get to bigger matrices, I want to actually show you one place where finding the inverse could be useful. And we're going to come back to inverse matrices throughout the course. But I want to show you one example where it's actually can be a little useful. To solve an equation, okay, let's go back to algebra now, pre-algebra almost. To solve the equation ax equals b. Now, some of you might think, oh, to solve for x, well, okay, divide everything by 2, right? Or by a, I'm sorry. Divide both sides by a. But instead of dividing by a, couldn't we also multiply by 1 over a? Basically, we take the equation, we multiply both sides by 1 over a, and we do that because 1 over a times a is just 1, right? They cancel out, and we're left with just that x. In other words, to solve this, we could think of it as multiplying both sides by the inverse of the number a. Well, let's consider a matrix equation. Okay, ax equals b. And I'm realizing now this b should probably be a vector instead of a capital B, but you get the point. To solve for x, one option here is, okay, we want to get rid of a. Well, unlike numbers, we can't divide by a matrix. There is no such thing as matrix division. But what we could do is multiply both sides by the inverse of a. Because remember, a inverse times a is just the identity matrix. And the identity times x is just x again. So notice that this gives us another way to solve a matrix equation. So let me show you an example of how this could be used. Consider this system of equations. Let's start by rewriting this as a matrix equation. So this is 3, 4, 5, 3 times x equals -2, 4. Okay. Now, let me take a step back. If I were solving this problem last chapter, yeah, I'm going to write the augmented matrix. I'm going to put it into echelon form or reduced echelon form. I'm going to solve it. Fine. I just want to show you another way to solve this. And by the way, at no point do I ever plan to ask you to use this method on a test. But if you like this method, there's nothing wrong with doing it. So if this is ax equals b, I can multiply both sides by a inverse. The a inverse times a is just the identity, so x is equal to a inverse times b. As always, my goal is to solve for x. So to answer this question, all I need to do is find a inverse and multiply it by b. Well, we know that a is the matrix 3, 4, 5, 3. So that tells me that a inverse is equal to 1 over, all right, multiply the main diagonal minus multiply the other diagonal. And then we're going to switch, let's see. So now we multiply that by a new matrix where we rearrange the old one. The main diagonal switches spots, but they're both 3s, so nobody notices. The other entries get multiplied by negative, so -4 and -5. And so A inverse is equal to 1 over -11 times 3, -4, and -5, 3. Okay, so there's my A inverse. So X is A inverse times B. So that'd be 1 over -11 times 3, -4, -5, 3 times B, which we've identified as -2, 4. So all I have left now is to do this product, right? My goal here is to find X. So to find X, all I need to do is find the product. Now, I'm going to leave the 1 over -11 out. We'll bring that in a minute. But here, I want to point out something here. Before this lesson, if I were going to do a matrix times a vector, I thought of it as that vector is the weights or the coefficients, and we put those in front of these columns. Okay, and that's great and that's fine. But I want to point out, we could also think of this as a matrix multiplication, right? Because a vector is a matrix that just has one column. Fine. So let's take my row, or my first row, and multiply it by the column. So I'm going to get 3 times -2 and -4 times 4. So -6 plus -16 is -22. Now I'm going to take my second row and multiply by my column. So we get 10 plus 12 is positive 22. Okay. And bring in the -11. And so my final answer is positive 2, -2. And there's my answer. So this allowed me to find X without doing any row operations, which is great, and that's fine. There's nothing wrong with this method. A word of warning though, this method was easy, easier if the matrix was a 2 by 2 matrix. Remember, inverse only works if it's a square matrix. So if A is not square, this method doesn't help. Also, if A is bigger than a 2 by 2 matrix, yeah, you don't want to do that. We're going to learn how to find the inverse of a bigger matrix in a minute here, but it's not as easy as the 2 by 2. So this method is not great if it's anything bigger than a 2 by 2 matrix. Okay, some properties of inverses before we talk about bigger versions. So the first property is that A inverse is equal to A. Okay. In other words, if you take the inverse of A and then take the inverse again, the result is just A. Let's see here. AB inverse is the same as B inverse times A inverse. And A transpose inverse is the same as A inverse transpose. So let's actually prove these. Let's actually show why these are true. And to do that, let's remember basically how we defined an inverse, right? A and B are inverse. Or let me write that a different way. B is equal to A inverse if A times B is equal to the identity matrix, right? You've got an inverse of A if when you multiply it by A, the result is the identity. So what I mean is this. This is basically saying that this is the inverse of A inverse. Okay? So, okay, hold on, how do I phrase this? This is basically saying that A is the inverse of A inverse. Okay, what does that mean? I'm going to take this matrix A inverse, and this tells me that if I multiply it by A, if I take this matrix that it's equal to, I should get the identity matrix. That was really confusing. Let me see if I can do better than that. Yeah, I'm going to do better than that. Let's try that again. Okay. For a minute here, I'm going to call this vector C. I'm only calling it C because B is already being used for other things. So C inverse is equal to A. Okay. What that means is that if I take C and multiply it by A, I should get the identity matrix, right? I'm claiming that A is the inverse of C. That means that A times C should give me the identity matrix. Okay, now, what was C? Well, C was A inverse. So I'm going to replace it with A inverse. Now remember, I'm claiming that this is true, but we're trying to show it. We're trying to prove it. So now let's take a look at this. If I took A inverse and I multiplied it by A, I'm definitely going to get the identity matrix, right? Because that's what it means to be A inverses. So what I found now is that C and A are inverses of each other, which means that the inverse of C is A. Well, that means that the inverse of A inverse is A. Okay, I think that's about as good as that's going to get. Let's do the same thing here. Now, one more time. I'm going to take this and I'm just going to rename it C again. Let's pick a different letter. Lots of letters out there. I'll call that D. Okay, so I'm assuming that D is equal to A times B. Now, I'm claiming that the inverse of D is this stuff. So I'm claiming the inverse of D is this stuff, which means that if I did D, not me, hold on. Okay, I'm going to try again. I'm claiming that the inverse of D is this stuff, which means that if I did D times that stuff, I should get the identity matrix. Well, now I'm going to take D and I'm going to replace it with what it's equal to. D is equal to A times B. So I'm going to do A times B, right? Just replacing D with what it's equal to. And then I'm going to multiply that by B inverse times A inverse. No, I'm not an ABBA fan. That's just the way it worked out here. And now let's do this product. Now, there was one property of matrix multiplication that does apply, and that was the associative property. It doesn't matter what order we do this product. So I'm going to start by doing this product, B times B inverse, because B times B inverse is the identity, because they are inverses. B inverse is the inverse of B. See, it's right there in the name. And then multiply anything times I, and the I just kind of goes away. And certainly A times A inverse is the identity matrix. So what I've proven is if I take D and I multiply it by all this stuff, I'm going to get the identity matrix. Well, that means that this stuff is the inverse of D. So that stuff is the inverse of A times B. All right, last one here. A transpose inverse is equal to A inverse transpose. Let's do this one more time. I'm going to give this a new name. I'm going to call it F. I don't know. I'm just a little weary about using the letter E. I'm going to give that the name F. So I'm claiming that F inverse is equal to all this stuff, which means that if F inverse is all that stuff, then F times all that stuff, well, I want to see what that's equal to, okay? If I take F and I multiply it by all that stuff, I should get the identity matrix, but let's see if that's true. So F was A transpose, so I'm going to replace the F with A transpose, and I'm multiplying that by A inverse transpose. And now I need a property from transpose. We get a property from transpose that said that AB transpose was equal to AB, oops, that should be an equal sign. Come on, there we go. A times B transpose was B transpose times A transpose. Well, look up there. I'm basically going from right to left. A transpose A inverse transpose is the same as A inverse times A transpose. I'm using this property at the bottom here from right to left. Of course, A inverse times A is just the identity matrix, and the transpose of the identity is just the identity. So when I did F times all this stuff, the result was the identity matrix, which means I guess this stuff must be the inverse of F, but that means it's the inverse of A transpose. Okay, so this is my proof. This is my explanation of why it works. These are all very weird. Let me erase some of my writing because I've got scribbles all over the place. These are a little weird, a little interesting, but yeah, they're just kind of interesting properties of inverses. Okay, back to our goal to find the inverse. We have talked about how to find the inverse of a 2 by 2 matrix. If we have a bigger matrix and we need to find its inverse, it's going to require more work, and it's going to require row operations. Yay! I knew we weren't going to go too long without those. For larger matrices, to find the inverse matrix, we're going to use row operations. We're going to create the matrix A and I, and in fact, I'm going to put a little line here. This is an augmented matrix. It's going to be different than the ones we've seen before, because the ones we've seen before, there was always only one column to the right of that bar that we draw. Here, it's going to be this whole identity matrix on the right side. Basically, the left and right sides will be the same, have the same number of columns, whereas usually what we've seen previously, the right side only had one column. So we're going to create the matrix A times I. We're going to perform row operations so that the left side reduces to the identity matrix. And when we do that, the left is the identity. Whatever is on the right side is that inverse that we were looking for. So we're basically going to set up this augmented matrix, and we're going to put it into reduced echelon form. So let's do an example. Let's find the inverse of this matrix. Again, we're going to create an augmented matrix. So we have 1, negative 1, 0, 1, 0, negative 1, 6, negative 3, negative 2. Oh boy, I wrote that wrong. Let's try that again. 6, negative 2, negative 3. And we're going to augment that with the identity matrix. Remember, 1's in the main diagonal, 0's everywhere else. And now we're going to do all the work to put this into reduced echelon form. Top row's fine. And remember, we're doing everything to all parts of that row. Basically, and I think we've had this conversation before, but basically the left side of that bar dictates what moves we're going to make. And the stuff on the right side just kind of follows along, and it goes along for the ride, and has the same stuff done to them. So for example, I'm going to take row 2 minus row 1. So I'll have 0, 1, negative 1. But I'm still going to do the same thing for all the right stuff, the right side of this matrix. So row 2 minus row 1 gives me negative 1, 1, 0. Let's do negative 6 times the top row and then add the bottom row. So negative 6 times the top row plus the bottom row is 0. Negative 6 times the top row is 6 plus the bottom row is 4. Negative 6 times the top row is 0 plus the bottom row is negative 3. Negative 6 times the top row is negative 6 plus the bottom row is still negative 6. Negative 6 times the top row is 0 plus the bottom row is still 0. Negative 6 times the top row is 0 plus the bottom row is 1. Okay. My first row is good. My second row is equally good. The bottom row, how about we do negative 4 times the second row and then add the bottom row. So 0, 0, 1. Again, negative 4 times the second row plus the bottom row is negative 2. Negative row times the second row plus the bottom row is negative 4. Yep. Negative row times the second row plus the bottom row is 1. Okay, continuing with my row operations, now I need zeros above all my pivots. So actually the first row is still fine. My bottom row is fine. And now I'm going to add the second and third rows. So I get 0, 1, 0. Again, add the second and third rows, give me negative 3, and 1. And then finally add the first and second rows. So I get 1, 0, 0, negative 2, negative 3, 1. 0, 1, 0, negative 3, negative 3, 1, 0, 0, 1, negative 2, negative 4, 1. Okay, and so what I'm finding is that A inverse, the left side is the identity, and the right side tells me the inverse. So it'd be negative 2, negative 3, 1, negative 3, negative 3, 1, negative 2, negative 4, 1. So we can use row operations to find the inverse. We could prove it's the inverse, right? We could do A times A inverse. I'm not going to, but you could do that to show that this does work, that when you do that product, you get the identity matrix. Okay, so that's how we find the inverse. Now let's consider a result of this. Notice that for this to work, all three columns and all three rows of A had to have a pivot. The only way that our matrix A was going to reduce to the identity matrix, that the left side of the augmented matrix would reduce to the identity, was if A had a pivot in every row and a pivot in every column. Well, if that had not been the case, then we would not be able to find the inverse. Basically, if A does not have a pivot in every row and a pivot in every column, then A is singular. A is not invertible. That connection, basically the connection between the inverse and the work we did in the last chapter, results in a really important theorem called the invertible matrix theorem. And in fact, we're going to introduce the invertible matrix theorem now, and then we're going to keep adding to it throughout this course as we learn more and more things. So the invertible matrix theorem says, let A be an n by n matrix. So right away, only square matrices. A is an n by n matrix. The following are equivalent. So all these statements, and I've got a bunch of them. I've got 9, I think. I've got 9 statements. All 9 of these are going to be equivalent to each other. So the first statement, A is invertible. Okay, this is why we call it the invertible matrix theorem. So A is invertible. Well, A is invertible is equivalent to saying that A is row equivalent to the identity matrix. If A is invertible, then we can do row operations to reduce it to the identity matrix. Cool. A has n pivot positions, okay, 1 in every row and 1 in every column. We just got finished talking about that. Think about the homogeneous equation. If I'm solving this equation, then it will only have the trivial solution. Remember, we said that's only going to happen if every column of A has a pivot. Well, that's statement 3, right? Every column has a pivot. The columns of A are linearly independent. Actually, that's the same as also saying, right? The columns every column has a pivot. That means that the columns are linearly independent, right? We spent some time talking about that in the last chapter. The linear combination that has A as the matrix, as the standard matrix, is 1 to 1. Same, right? This is the same thing. 1 to 1 was equivalent to saying that the columns were independent, et cetera, et cetera, et cetera. The equation AX equals B has a unique solution for all B, okay? That's the same thing. Actually, that's saying 2 different things. That's saying that it's a unique solution. Okay, great. That's 1 to 1, right? That the solutions are unique, but it has a solution for all B, right? There is a solution no matter what B we pick. That is another way of saying that the columns span R, N, and that is also the same as saying that the mapping is onto. There's a lot going on here, and most of these things we have already talked about, and we've already made a lot of these connections. The big difference is now we're only talking about square matrices, and we're now throwing in that extra property of invertibility because the number of pivots and so on depends on that invertibility. Now, to help us organize this a little bit, because again, some of these things are linked to other things that we've discussed before. I've got this kind of flow chart here. If it helps, great. If not, so be it. If A is invertible, it's row equivalent to identity matrix. We saw that when we found the identity. There's a pivot in every row and every column. We talked about that. If there's a pivot in every row, that told us that no matter what B we pick, there is a solution. No matter what B we pick, there's a solution. That's the same as all the columns span all of Rn, and we call that an onto transformation. If there is a pivot in every column, now we said there's at most one solution, right? If there's a pivot in every column, that means that let's see, if there's a pivot in every column, that means that there are no free variables. So we're going to get no more than one solution. The columns are linearly independent, again, because there's a pivot in every column. Ax equals 0 has a trivial solution. And if there's at most one solution, that's what we called one-to-one, right? If we map to B, that mapping was unique. All these things, basically this column and this column, these all are directly related to what we did in the last lesson. This is just kind of tying it all together, specifically for square matrices, specifically for invertible square matrices. So let's consider this example and let's ask, is A invertible? Well, now we have like 9 different properties that are all equivalent to saying that A is invertible. Probably the easiest one is to find the pivots. If A has a pivot in every row and every column, then my answer is going to be yes, it is invertible. And if it doesn't, then the answer is going to be no, it's not invertible. So let's take A and let's reduce it. Okay, and again, all I need are the pivots. I don't even need reduced. Please notice the last example that we worked through said find the inverse. So now you need to augment with the identity and reduce it, reduced echelon, etc. This problem just wants to know, is there an inverse? So to answer the question, all we need to do is find the pivots. So the first row is fine. -3 times the top row and add it to the bottom. The second row, we get 0, 1, 4. 5 times the top row plus the bottom row will be 0, -1, -1, I believe. Yep. And then add the second and third rows. We get 0, 0, 3. Okay. So 1. Pivot in each row and column tells me that A is invertible. Okay, and that's it. And that's all we need. Hey, there's a pivot in every row and column. Cool, I guess A is invertible. Okay, one more thing that I want to mention briefly. I mentioned briefly the idea of when you learn functions back in pre-calc, we talked about F inverse, the idea that F of F inverse of X was just X, right? The F inverse is kind of undoing F. So if F is raising something to the second power, then F inverse would be the log base 2 of X. They cancel each other out. Okay. I might have picked a really complicated version, but you get the point. They undo each other. Well, let's say that A and B are inverses, which means that the product results in just the identity. Well, two transformations, T and S are inverses if, again, I undo each other, right? The same as with functions. Applying T or applying S and then applying T to it results in just the inside stuff, and vice versa. Well, it turns out that if A is the standard matrix for T and A inverse is the standard, then A inverse will be the standard matrix for T inverse. So inverse linear transformations have standard matrices that are also inverses of each other. So it's just an interesting property. I don't know if that helps us any, but who knows? Maybe it will. Anyway, that is the end of the lesson. Thank you very much for watching.